analogously, what I did before for the dimension, one dimension, I will extend the idea of self-adjoint operator to the three-dimensional space, and I will use the Green's identities. Okay, that's a very important mathematical tool. Okay, to obtain what I call the Green function. Look, till now, I'm not solving differential equation. Okay, I will do this later using the Green function G, and I will tell why I'm using the Green function. Okay, now let's do the development of the Green's identity. Okay, these here are the mathematical tools, okay, to use to obtain the Green's identity. Now, a gradient of a scalar function phi, okay, is a gradient of phi is a vector quantity. Okay, look, in the Cartesian coordinates, the operator is a gradient here. This is equal partial with respect to x, I plus partial respect to I, j plus partial respect to z, k. Okay? This is an operator. Okay? There's a vector operator. In general, it's called a pseudo vector. Okay? Because it's not a vector, it's an operator. Okay? It behaves like a vector if I plug this operator in a scalar function. Okay? Now here, the scalar function phi, there's a vector. Okay? There's a first order tensor. Okay? The scalar is a zeroth order tensor. Now, divergence of a vector. Okay? I can have divergence of second order tensor. Okay? But this divergence of a vector is, in this case, okay, the dot product between this operator, okay, dot the vector v, okay, or v or f, doesn't matter, okay. This is a scalar quantity, okay. This is a zeroth order tensor. And here the theorem of Gauss, okay, that relates the integral of the closed surface to the volume, okay. Here's a volume V, okay. This is a surface. There's a vector, okay. There's a normal to the surface. This is a modulus, okay, of the vector ds over here. So this is a vector ds. Okay. If I integrate, okay, in the whole surface, the closed surface, okay, f dot ds, this is equal integral in the whole volume of divergence f df. Okay. Now, and this is Laplacian of a scalar. Okay, there's a scalar function. Phi. This is gradient of the scalar. This is a vector. Okay, vector. Divergence of a vector. Okay. This is the Laplacian. It's called Laplacian of this scalar function. We're going to use this. Okay. So these are the tools to develop the Green's identity, just to find out self-adjoint. The idea is the same ideas like we have been used, okay, for the first video to this one. Okay, now let's do this. Consider a vector f is equal, this is a scalar function, okay, gradient of u, okay, u, v, r functions. You see, I will substitute, I apply the Gauss theorem over here, so integral of the whole surface of f, this is v, gradient vu, dot ds, alright, here. This is equal integral over the volume, okay, divergence of this vector v, okay. V is a variable, u is a variable, okay, dv. Now, by definition, okay, the direction derivative for our u with respect to n, this is equal to the gradient of u, that's a normal to the surface, okay? This is normal to the surface, okay? Then I can write the vector ds as n ds. So the left hand side over here, okay, this is integral of s, in this case, of v partial u respect to n ds, okay? Because I substitute, okay, the gradient of u dot vector ds, okay, is normal times the magnitude of the vector, and this by definition, that's a directional derivative, okay? Directional derivative. Now, okay, now I developed, okay, remember that the operator, okay, this is derivative operator, okay, I see this as this derivative will apply to this function v and the vector, okay. Those here are function of the position, okay. Now I would like to emphasize here is this. You see, the whole equality we see here, okay, does not depend of the coordinate system, okay. This can write down the Theorem of Gauss using cylindrical coordinates, spherical coordinates, you see, and this is doesn't play with a specific coordinate system, but I can use, okay, this relationship, for instance, in Cartesian coordinates, in spherical coordinates, doesn't matter. Like this is the gradient, okay, operator, okay, using its component in Cartesian coordinate, okay? This is not a definition, it's not a definition of gradient, okay? This is a particular case where I use the Cartesian coordinate system, okay? Now, this is derivative, so I can develop this. There's a volume, okay? Now, I will have here this identity times u, okay? dv plus this is C. Now this is V divergence of W dV. Okay? This I will erase it here just for okay. Now I will do the same, just exchanging U and V over here. So I will have integral of the closed surface of U dot ds. Okay, this is equal. You see, over here, just use the direction derivative of U partial V with respect to M ds, except what I did here. This is equal integral the volume. This is divergence of the vector U. You see, I just exchange U and V over here. It's the same. So my F here will be U gradient of V. Okay? This is the vector F. Okay? Now I'll develop the derivative of a